Introduction to Quantum Physics. Click up here to watch part 1 where I explain the origins of quantum theory. In this episode, we will start by looking at the very weird and famous Double-Slit Experiment. Imagine that we have a gun that shoots marbles and another that shoots waves, and that we are going to shoot them at a wall that has 2 slits. If we shoot the marbles towards a wall with 1 slit covered, we see that almost all the marbles will go through the open slit and land on the wall behind it. If we do the same but with both slits open, we observe that the marbles will land equally on both sides. If we fire waves at the 2 open slits, instead of marbles, we will get a wave pattern. However, if we carry out the same experiment using electrons, elementary particles in the subatomic world, instead of marbles or waves, it gets very strange indeed. If we cover up a slit, we get a pattern of electrons on one side of the screen, just like we observed happening when we fired marbles. When both slits are open and we fire electrons, we get a very unexpected behavior. The weirdness begins because we get a wave pattern. The electrons behave like waves instead of particles. If we observe the experiment, it gets even stranger. Scientists decided to test the hypothesis and place a piece of equipment to see which of the 2 open slits the electrons passed through. And incredibly, the electrons behaved like particles again. How is this possible? How do electrons know if they're being observed or if both slits are open? Does this cause them to act in a different way? Scientists have accepted these findings by thinking that electrons can act as both particles and waves. Yes, this is very similar finding to the wave-particle duality that I explained in part 1 of this video. The difference is that the double-slit experiment also shows us that the duality applies not only to light but also to subatomic particles such as protons, neutrons, and electrons. The Schrödinger's cat experiment helps us think about how the act of observing changes our world. This was a different kind of experiment, what we would call a thought experiment, meaning that it happens in the mind of a scientist as opposed to in a lab. So don't worry, no cats were hurt. Austrian physicist Erwin Schrödinger hypothesized putting a cat in a box with some poisonous gas. Using a mechanism activated by radioactive particles, the flask would have a 50% chance of breaking and a 50% chance of not breaking. So there would be a 50% chance that the cat would survive and a 50% chance that it would die. So Schrödinger concluded that before the box is opened, the cat is alive and dead at the same time. At the same time. It would only be our action of looking that would make reality collapse, and only then we could observe if the cat would be alive or dead. This experiment suggests that when we look inside the box, nature is forced to decide the state of the cat, dead or alive. This is mind-blowing. Similarly to Schrödinger, Werner Heisenberg helped us understand how the quantum world is regulated by an uncertainty principle. He demonstrated that it's not possible to be 100% certain of both the speed and the position of a subatomic particle. If, for example, we know the speed of an electron, we cannot truly know its position, and vice versa. When we use a microscope, you must fire a photon to see what is happening to the particles, so the photons will collide. This is because when we look, no matter how small and precise our equipment, in the quantum world, which is so very small, we can't avoid disturbing what we are looking at. Quantum entanglement is the term used to describe the correlation that exists in certain situations between two or more quantum objects, such as a pair of photons or electrons, regardless of the distance separating them. To put it more simply, entanglement occurs when a pair of particles interact physically. When they become entangled, they remain connected even when they are separated by vast distances. Again, this behavior could not be described by classical physics, but could be explained by quantum physics. Whatever happens to one will happen to the other. If you do something to a particle on Earth, the same thing will happen to its entangled particle on Uranus. This is mind-bending! I hope you found this video useful. If so, then please like it and subscribe to the channel. See you next time!